Próba mikrofonu, raz, dwa, trzy, raz, dwa, trzy, raz, dwa, trzy. Czy mnie słychać na streamie?
Guys, can I have your attention? So it's 7 p.m. Let's start with opening remarks for today's meetup. And we're very proud that it's our 7th meetup. So some of you might recall us. We are Cracow Robotics and AI Group. And yeah, we're making this event every 2 months. And we're pleased that there's so many of you right now with us. And so for today's agenda, we'll start with a developing test bench for Space Rover, a case study by Tomasz Hełminiak. He's going to tell us his own experience in Germany building a test bench for a Space Rover. You're going to get more details when when he will present it, but I'm pretty sure it's going to be a great talk. Later, around 8 p.m., we will have a short break for a beer and networking. Later on, and a dog, of course, because some of you, well, I'm pretty sure you saw it. I'm not sure if it's visible on camera. Anyway, and later, the representation entitled Where Are We Heading? Path Planning Methods for Every Occasion by Bartłomiej Bonar. He will take us his experience he gained during his PhD, ongoing PhD, about path planning. And well, we can say it's his robot right now. It's his robot right now. AGH let him, so yeah, he's responsible. After that, we'll have short, like a few minutes for lightning talks, and of course, more time for networking and beer and dog, obviously. So here you have QR codes for our meetup, which, well, partially the QR code is hidden behind me in the camera, and also our robotics Discord. We try to kick in like some robotics community around here. What else? Our great sponsors. First of all, well, let's start with a round of applause for techies, because the meetup wouldn't be here without them. Techies, well, Codete is a software house, and Techies is this place we're right now here. They are supplying us with the first beer, cool, well, not badges, I don't know, well, anyway, vouchers, everything in here, also the stream, etc., is next to them. Also, Huzarion, who's sponsoring sponsoring the second beer. If you want to grab another one, go to the bar and ask for a second beer from Huzarion, and you will get it. There's limited supply, just so you know. And of course, a robotics newsletter, Weekly Robotics. They provide us with every week. You can find there more cool information and the news from robotics world, from, well, around the world, robotics information, cool papers, cool projects, everything. What else? So I guess we can start. Tomasz, come here. The microphone is yours.
Okay, so hello everybody. My name is Tomasz Chełminiak, and today I will. Oh, okay. And today I will give you a presentation on the project I did. So developing the test bench for a space rover. First, couple of words about me. So I'm a mechatronics engineer, very passionate about space, especially robotics in space. But also I like very much electric cars, also especially in space. So yeah. So quick agenda for the presentation. First, I give you some background and concept for the project. Then I will tell you a couple of words about the design of the test bench, and then I will tell you about testing, validations, and then give a quick summary. So some background. The project I did was my master thesis at IGH, but also the project was realized at German Aerospace Center in the Institute of Dynamics and Control, and it was a part of a Scout rover project there at DLR. So quick overview about the rover itself. So this is a special type of rover designed to traverse through difficult terrains, explore some caves and hard to reach places on Mars and Moon. And it is quite robust. It has a failure-tolerant design. It has a special type of rimless wheels that combine walking and rolling locomotion. And it has 6 wheels with 6 actuators, so 1 actuator for each wheel. Okay. So kind of what was the goal for the project? So I was given a task to kind of design some simulation environment, the test bench to test this special rover, the Scout rover. I needed to create a concept as well as to design it and then later perform some tests. So first, let's take a look what are the ways to actually test a rover. So of course we can, if you already have a prototype, we can take the rover outside to some simulation of the terrain. So we either can take it on some trip, or we can have some dedicated place with rocks to train and test subsystems. But also it is often beneficial to perform some tests in laboratory. And here I have some examples of laboratory tests with just a single wheel, which is quite common for rover testing. One interesting example is also a DLR project. It's called Troll, and this is testing of the wheel, but the wheel is attached to the robotic arm to like a big industrial robot. So you can vary the load and have more degrees of freedom than in a more classical testing bench. And here's also example of a single wheel test of a Scout wheel. It's kind of some early prototype because it's slightly different than the one that it's used now. As to the concept of the test bench that I designed, I wanted to also have it in laboratory, but also I wanted to test the system as a whole. So not only test one wheel, but test like all the actuators and also simulate well the load that the rover encounters in normal situation, in normal operation. And also testing in the laboratory, the whole rover gives the freedom that you don't have to use batteries, so that the test can be done longer. So the concept that I came up with is similar to testing the motors. So basically, one motor is attached to the other to act as a load. And here I also wanted to incorporate the belt systems to kind of so the system is better laid out, so one motor can be on top of the other. and also it allows for some variation in ratio, so for different gears. And you know, here also I have the concept. Maybe I don't know if you can see my mouse. Maybe it would be easier. So here we have maybe like this. Here we have the main computer of a test bench, and it is fed with a load profile, so the kind of command load. Then computer commands the torque to the motor, and through the gearbox it's and the belt system, it goes to the scout rover, and here it's acting upon the motor. And here this motor is targeted at torque, but the rover's motor is targeted at velocity. And here's also a possibility for some data exchange for a better control of the whole setup. As for a motor selection, no, sorry for this. As for a motor selection, I selected the BLDC servo motor with planetary gearbox. So I try to match the capabilities of the rover, but also kind of outmatch it, so it's stronger than the rover's motor. For the belt system, I decided to go with a timing belt and 1-to-1 ratio of the pulleys. They are designed to be 3D printed. However, possibly in some future designs, it can also be done from aluminium or some more durable material. But for initial prototyping, 3D printing is quite decent. Okay, maybe let's go back. I forgot to mention that the motor is running the EtherCAT protocol. And here I have like a slide. What is EtherCAT? So basically, it's a communication standard. It's high speed. It's real time. It allows for setting up the devices in a chain, and it's used commonly in some industrial application and robotics. And yeah, I mainly went for the EtherCAT because at DLR it's quite common in projects to use the EtherCAT. So I knew that there are some experts that can help me if I come into some troubles. And yeah, I did a bit, so they saved me with that. As to CAD design, this is kind of a final design of the whole test bench. So starting from here, for the mounting system of the pulleys, I designed it so it can be easily swapped with the wheels. It's mounted the same as the wheels of the rover, so we can easily take out the rover from the field and unmount the wheels and mount it to the platform. Also, we have some features as clamps and aligners, so that the rover is secured and in place. And also there is simple tensioning system to tension the belt. Here I have the electronic scheme of the whole project. So as I mentioned before, in EtherCAT we can connect devices in chain. So here we have a main computer, and then the EtherCAT communication goes through one motor and to the other, and etc. Till the end. And all motors are powered via one power supply, and there is separate power supply for a rover. This is a variable one, so we can simulate some other scenarios like low battery and some other cases to test it in different scenarios. And also, whole system is connected to some Windows PC to allow the remote control of the whole setup. As for the software, it is running on a kind of regular PC running Debian, and it was written in C code. And special EtherCAT library was used there. And for some components of the code, maybe this is bigger. Okay, so here is kind of a main function. It kind of coordinates all the system and processes, and then here we have two separate files and functions for controlling both motors, the loading motor as well as the rover motor. The rover motor is here controlled by the test bench, because this setup was realized in a prototype, but in kind of a final setup, the rover has its own control system. So this is why it's in dotted lines. And here there are some other function for some saving data from the test bench or communication with a rover, and also loading load profiles. As I mentioned already, I also did some prototype, because the system kind of consists of 6 similar setups. So for each wheel, for each motor, there's another motor. So I decided to go first with a smaller setup to just test the capabilities. As you can maybe notice here, the ratio of the belt is slightly different. It is because the motor is with slightly different gearbox. It's just that at the institute there was such motor available, so I had to kind of scale the belt system to incorporate those changes. And I think that's the main differences. I mentioned before that both motors are controlled via the main computer, the test bench computer. Yeah. Okay. Here's some demo of kind of a verification of the prototype. So here, this is some tool from DLR allowing for live signal monitoring. So here I applied some load profiles, and you can see how the prototype is working. It's maybe not very impressive, but it was quite a lot of work to make this 2 small motors move. Okay, so I mentioned already about load profiles, and maybe this sounds kind of enigmatic. So I decided to simulate the loads on the test bench by first gathering some data from the rover itself. So I did some experiments, some kind of systematic runs of the rover to gather some loads. On example here, we can see here on the green is a speed of a wheel, and here we can see the load. So here I tried to control the rover so it's going with a constant speed, and here I recorded the torque on the motor. So this on red is kind of a snip of the recording, and this I later used as the load profile. And all those testing I did seen here on the picture, kind of rocky field for testing. I mostly use the flat parts to kind of don't overcomplicate at the beginning. And here I have some recordings from the testings. This also on a different place where it's more kind of a volcanic sand environment, let's say. So I also have some load profiles generated there. In total, I generated 16 load profiles for different terrains, so stones, sand, and with different speeds, and also backwards, forwards, and also the rover is capable of moving the spokes in synchronous way and asynchronous way, and there are different kind of shifts. So I also did some load profiles on different shifts, phase shifts. Yeah, to the validation. So yeah, the validation for me was to kind of prove that if I fit the load profile I recorded to the loading motor, it applies the load. I kind of calculated a special formula to convert one load to the other, incorporating the gear ratio and the belt. And I wanted to kind of compare the input to the output, so they match to each other. And here is example on load profile 2. As you can see here on the right, it doesn't really look like it's matching. There's a lot of noise. So it didn't look very promising. However, I tried to filter the data. And fortunately, after filtering the data, I saw correlation in most of the good correlation in most of the profiles. As to the noise itself, I unfortunately didn't really get to the clue of why the noise, such high noise was happening. It was probably due to some electrical issues or maybe something in the measurements. Unfortunately, didn't have enough time to investigate it properly, but I managed to prove that that the loading torque that I'm applying is really also kind of seen by the motor, the rover motor itself. And yeah, to summarize it, the validation was successful. I had some issues with the noise, but kind of I managed to show that it's really working. There were some challenges, like I mentioned, noise in the data, also some mechanical failures. Mainly I mentioned that I used 3D printing, so sometimes it happened that like the pulleys just broke. A lot of code troubleshooting, especially with the EtherCAD. It's quite tricky to implement it, and I had a lot of troubleshooting with just moving the motors in the correct way, and then after that it was much quicker to develop the functions and control itself. And also you may have noticed that I didn't show the full test bench constructed. It's because I didn't manage to assemble and test the full test bench due to some time and cost issues. I kind of didn't there wasn't enough financing at the time to finish the whole test bench. And for some future development possibilities, maybe just some ideas. I'm not working on a project anymore, but for sure it would be nice to kind of construct and see the final test bench. Also, I just did it from some rough scripts and running it through SSH. So it would be also nice to have some nice GUI to be able to do the testing kind of more user friendly. And also it would be nice to have some more advanced load profiles with more terrains, more speeds, etc. And also, while I looked at all the load profiles, they're quite repetitive because, of course, there are variations due to terrain. However, you have those 3 spikes, so you see kind of the frequency of the spikes. So you see also in the signals that it's going like up and down as the spikes. So maybe there are some possibility to kind of find some synthetic function to then perform some more advanced simulations. And that's all. Thank you very much.
Thank you, Demek, for the great presentation. Now we have quite some time for questions. Okay, here we got a first person.
I'm just curious, maybe it's a side topic. With this kind of wheels, the rover, apart from going forward, is going up and down. Is there any way to address this? Like it's energy wasting, or I don't know, actually.
Yeah. The components of the rover. I don't know if I have some good slide, but maybe we can show the recordings again. The components of the rover are connected with kind of a flexible material, and of course, while doing the testing, I only recorded kind of one load of the wheel. So I kind of ignored the system, like kind of the dynamic system as a whole, and only recorded small part of it. So there are some approximations. but yeah, maybe if you record each individual wheel from the test, you can see also on the load profile the differences in the load when it is moving. But when it comes to reproducing it on the test bench, yeah, I think with colleagues there we had one very wild idea to kind of attach to each wheel kind of a robotic arm and then move it up and down from all 6 sides. But it's like very complicated and and crazy. But yeah, maybe.
So on this video, I can see, as the colleague before me said, the robot is moving up and down. Have you tried controlling the motors so that there's a phase shift between the spokes of the wheels, so that at any given time, like 2 spokes touch the ground and one? Do you know what I mean?
Yes, I know. Yeah, I think I tried different phase shifts, but yeah, I don't remember exactly which I tried. I know that there were some that the rover was really like jumping a lot, especially with the higher speeds. It was like very shaky and random movement. So I'm not even sure if you imagine going this to the Mars or to the moon, it going like very fast, because probably if you are traveling through some caves, you want to move very slowly. And also that is how the rovers move now, but it is also due to the fact that there's a latency because we are controlling it from Earth. But maybe if we will be controlling it from the moon or from the Mars, and it could be different. Yeah.
All right. I have another question here.
Oh, here, okay.
I'm thinking about the design, and it seems like you can increase the amount of modules in this centipede, because this is how I perceive it. What would be the exact role of this rover on Mars, except of pathfinding? Can you find some other applications to it?
I think just mainly for just exploring the caves, because and some maybe terrains that are hard to reach by kind of a big rovers, and also for a human, and we can also attach a lot of sensors and everything to the rover, so we can then map the terrains or like some underground terrains. But what else? I see that if the rover is designed in a way that it's quite cheap and robust, you can maybe also use it as a kind of you send it first before like the very expensive and big rover, and it checks if it's safe or not. So it's kind of scouting for for the big rover. Yeah.
I have another question. So everyone is asking about design, but this project was mainly concentrated on the test bench or this testing for motors. And I'm curious, what was your main goal about this test bench, and why you didn't just skip to the field tests?
Yeah, the goal of the test bench is to, as I mentioned, in general, if we go back, the first reason was that at the institute they wanted to have a way to test the rover in laboratory. So, and the reason for that is that often here for example, as you can see, there are rocks like just next to the institute. So maybe it's still kind of easier than going somewhere on a trip. But still, when I was there for kind of half a year, they only did those tests of the rover, I don't know, 2 or 3 times, because it's kind of a lot of preparations to do it. And also, the weather is not always perfect. Sometimes, raining, snowing, etc. So yeah, it may be difficult to test. And other thing is, you may do some tests here first, and while doing some path and some maneuvers, there is some failure. Something happens, something with the motor or with the software. And when you record the data, you can then try to reproduce it in the laboratory, the exact recording you did, and maybe it would be easier to find kind of a root cause of an issue instead of just trying to maneuver the rover. Especially, maybe I didn't mention that the rover is controlled, at least at the point that I was doing that manually with the controller. It doesn't have any path planning or anything, at least so far. So also it's helpful in that matter. Yeah. Okay, so there's question from the chat. Why 3 models? This honestly, I have no idea. I didn't design the rover, only the test bench. So yeah. All I know is that that it can be more or less. It's designed in a way so it could be like, longer, shorter. Yeah, for sure it would be difficult to have just one and maneuver it. But yeah. Also, I think it maybe I saw some cases where one of the motors or kind of even more motors just failed, and it still was able to move with 2 motors immobilized. So perhaps they did some analysis that this is like kind of an optimal number. So even if some motor failed, it can still go further. Yeah.
Okay, have you thought about what about the lack of the signal inside the cave if the robot is supposed to explore a cave? So how can we address this problem?
Yeah, there were some discussions about it. I were on a couple of kind of brainstorming sessions for the rover design itself. And yeah, probably the main idea was to like just have some kind of repeaters of the signal to kind of maintain the communication. But yeah, just some ideas. There's no real plan so far, as I know.
Thanks for the presentation. So I have 2 questions. First one is technical. What is, I don't remember the exact name, but this MLNet, ModelNet, something like that.
Oh yeah, okay. Yeah, so let me go back. It's good you ask. I forgot to explain it. So good question. Yeah, here we, for example, can see the ModelNet. This is kind of some library, some communication protocol developed at DLR that is used to communicate and to gather the data from the rover. And also, I think it's used for some other project also connected with robotic arms, etc. And I decided to incorporate it to also be able to communicate with the rover itself. In a prototype, I didn't really use it. However, in a final kind of test bench with the rover attached, it would be good to also have some data from the rover. And it is possible thanks to this ModelNet. As to some technical details, how it works, this unfortunately I don't know. If you're very interested, I can try to ask or find some information. But yeah.
Thanks. And I have second question about the, let's say, future of this project. So, like, what do you see the Scout as some sort of a prototype that will, let's say, that have no chance to like be incorporated in a real mission, or do you see it as a robot that eventually could be incorporated in mission.
Yeah. Okay. So for sure, as of now, it doesn't have any specific mission. It's only developed as some proof of concept. But with all those talks that we want to go, to the moon and to the Mars, I see it's possible that something like this would be useful, especially that is very, I would say, untypical type of rover. At least before working on this project, I haven't heard of those kinds of rovers. You only see those like kind of big science rovers on Mars, but this is something different. But I'm not sure if it's good as a standalone mission. Maybe, as I mentioned, it would be kind of a companion to some bigger robots. For example, as you have now the robot with a helicopter, so maybe you would have robot with a helicopter and small kind of scouting rover. Yeah, but maybe also this guy can do this. So yeah, I don't know.
Okay, I have here another question. Congratulations for your efforts for this project, first of all.
Thank you very much.
Big kudos. But I have less technical question. Have you worked on this project alone, like on this sub-project connected to test bench, or did you cooperate with some other researchers? Because I know that one of my colleague, older one, had some research and work on his master thesis on this exact same model of the Scout rover at DLR. So just curious that if you worked alone, or was that some kind of structured cooperations between AGH and DLR?
Okay. So first of all, yeah, I met your colleague Adam at DLR. He was also there doing a PhD later. But yeah, this project was like kind of completely mine. I mean, the test bench itself, the rover is a separate project of the DLR, and they just kind of find some students to do some kind of side project or some like more development. And there was also not really any cooperation of like kind of, I mean, at least not official one between AGH and DLR. It was just my supervisor kind of got me in touch with people at DLR, and I just made an agreement there. But yeah, and also it happens that I did my master at IGH. Yeah, but of course I kind of used a lot of help from some colleagues there at DLR. If I had some difficulties, we discussed it and they helped me. But in general, the test bench itself, I was designing by myself.
Thank you.
Hello. Did you also capture multiple mode dynamics of different types of terrain, or just for single type of terrain, like sand with rocks, small rocks, big rocks, stuff like that?
Yeah, so I had, I think I had two types of kind of smaller stones or rocks. Then I had some bigger rocks, and also sand. And also I think I did some part on some flat floor, like completely flat surface. And yeah, I think that's it. Maybe I have some extra slides, and oh no, but there's no details. But you can see here there are like stones, sands, flat surface, and you can also see some speed. So yeah, and also those are the only kind of good ones. I did a lot of like some random ones, and yeah, a lot of testing. But it was fun because I was just had a joystick and was like riding the rover around. So
Yeah, no, but the question was who defined these load profiles and if they incorporated like multiple dynamics, like for example, if you have small rocks on top of sand and stuff like that, because that's more realistic to what you might find in the terrain.
Okay, no, so I didn't do any kind of different combined terrains. Also, it's just those load profiles are basically quite simple because I just had some straight path with rocks, and then with the constant speed I went with the rover. So it's again, it's some kind of approximation of the load. It's not ideal because of a lot of conditions. Yeah, because the system is also very dynamic. It's flexible, so it's it's difficult to simulate it very precisely. I know at DLR they're also working on simulation of kind of particle simulations, and I think there are some plans to future to maybe simulate the rover itself in some virtual simulation, and then use this platform, the test bench platform, to apply the real load. But it's there's a lot of ideas, but yeah, we will see.
Any other questions from the audience? Oh, there's one.
Thank you for the talk. You just tell that there is some particle simulation going on. Would like to ask what kind of particle simulation this is. Did you have every grain of sand as the object, or there is some approximation to it?
I haven't worked on it directly, and unfortunately, there is no the colleague we mentioned before, Adam, that I met at DLR, because he's working on it, so he probably would tell you some details. But yeah, unfortunately, I don't remember. I think that there are some approximations to the shape of the particles, but yeah, I haven't worked on it and haven't really used it. I only seen some maybe demos, and I know that they are doing something like this, but don't have any details, unfortunately.
Yeah, one more quick question from my side. Did you have any requirement to make this test bench reusable for different types of robots?
It was made specifically for this rover, especially that this rover is kind of special with those special wheels. But also I can see using this test bench for some regular rover, because the concept itself is quite simple, because you just attach one motor to the other and apply some load. So yeah, probably you can scale it. It's all the matter of just picking the right motors, and then also designing the right kind of enclosure and kind of attachments for the rover. But also designing this, I knew that they are developing the rover. So for example, the motors, I think I picked kind of more powerful motors to the rover than it's required, but I knew that there are some talks that they will be replacing the motors in the rover for some newer ones. So I a little bit anticipated for some changes, but not very much.
Do we have some more questions, or not really?
There is a question from me about the whole project, probably the most tedious part. There was a lot of topics involved: hardware, terrain, software. Which of them was the most problematic? Which was the most difficult to debug?
Yeah, I think the most difficult topic was software, especially as I mentioned a little bit about controlling the motors itself. So the challenge was not really to, for example, finding the right formula to control it, or control kind of in a more higher level, but just moving the motors was tricky. I had a lot of issues, especially with the Scout motor. For some reason, it was really tough to communicate with the motor controller on this side. So I had a lot of troubleshooting, and I think that especially I had problems with not really moving the motor, but also with a feedback. So getting like some measurements from the motor, the data was looking very very chaotic, and also you can see the problems with the noise. So it's still some of this remained, but yeah, I think that the software was the hardest.
Yeah, I was about to ask you for a round of applause for Tomasz, but you did it yourself. Anyway, also thank you so much to all of you for asking so many questions. And yeah, right now we will have a break for a beer. Also, you can check out the robot, talk to guys that are responsible for it, and yeah, have a great time. We will be back in, let me check, in like 30 minutes or so. No, half an hour, right? Half an hour with another presentation, like second presentation. So yeah, have a good time. Enjoy your beer. Okay, can I get your attention? So, if you mind, let's slowly sit down, and we will be starting with next presentation. This presentation will be about path planning, and the title is Where Are We Heading? And Path Planning Methods for Every Occasion by Bartłomiej Bonar. And as I said, this part of his experience while doing a PhD at AGH, and of course is quite connected, as I understood, with this beautiful robot. So let's give a round of applause for Bartek, and we're ready to start.
You hear me? Okay. Hello, everyone. I hope you don't mind me sitting. I'm not really a standing person. I much prefer lower energy levels. Hi, Mom. So, path planning. At the first moment when I was preparing for today, I was thinking about making a survey on the methods, but I realized that it would be, well, a bit boring, and also there are many people who will do it much better than me, and those are already available. So I decided that I will try to tell you a story, or like scientists like to call it, a case study. So let's imagine that we have a factory, and inside that factory we have some machines, and with those machines is working Bogdan. Bogdan is a technician that he's doing a great job, but at some moment he realizes that he needs more materials. And there is no way that Bogdan will carry them himself. He has some health issues, he has really bad back, but luckily for him, the place he's working at is an intelligent factory with a fleet of logistic robots. So if he needs something, he can just call to the central and ask for more of them. After some required processing, a logistic robot will be dispatched. Robot will be dispatched first to go to the warehouse to pick up all the needed materials, and then the robot should be able to go to the Bogdan to deliver it. But regrettably, the life of a robot is not exactly as simple as everyone would like it to be. Because on his way, he's met with obstacles, dangerous object, and worst of them all, bills. So now the question arises, what the robot can do, what the robot can do to go around all of them and reach his target. Especially since the deadlines are coming and the temperature is rising. So to begin with, I will try to make a simple differentiation between different types of algorithm, different levels of abstraction, and just my point of view, how we could navigate in the whole path planning field. So let's start with a definition. There will be only two, I promise. So the path planning can be stated as, path planning problem can be stated as finding a safe, obstacle-free road from initial state to target. And what exactly it means is a lot. Depending on context, on situation, on level of autonomy that we are talking about, the complexity of the problem may vary very much. But the basic considerations that we can take into account are whether the environment that robot will be working in is known, whether the obstacles are moving, so the environment is dynamic or is it static, whether the terrain is human-made, because in such a situation we can assume that way is somewhere there. If we have robot that, for example, should go into the jungle, then we have no idea whether there is any feasible path. And yeah, is there even a way? So after taking those into account, layers of abstraction. I don't believe this is any official table. This is more something what I developed through talking with people and looking at the problem from the perspective of person that has to program it later. So it's more practical approach. So to begin with, we have a cognitive level. So going back to the case, this is the moment where Bogdan called the central and said that he needs some materials. So the case he stated was deliver me something. And then there needs to be some system, or it would be good if there is some system, that will translate this request into some sequence of tasks that can be later performed by robot. Then comes the global path planning. This one is usually performed offline, so before robot even starts moving. And based on the known geometry of environment, known conditions, it will be trying to find the best path for the robot to travel to realize the task. Also, at this point, we are usually talking about optimization. Local path planning, this one is mostly done online. So while the robot is already traveling, and local path planning comes into play when, while a robot is already traveling, he's met with some unexpected situations that he has to address. For example, the pre-planned path is not feasible because of reasons, because of some obstacles that were not previously known, and it detected it just a second ago. And the question is what to do now to somehow navigate around them. And then there is the last level, motion controller. So this one, based on the path that has been already prepared, is translating this into the trajectory. Trajectory is path with some timed conditions. So we are talking not only positions, but also velocities and accelerations. Types of algorithm. This one is tricky because depending on the source that one may use, some algorithms may fall into different categories. Classical algorithm, the most common definition is that those will search all possibilities until finding the optimal solution at some point. And this part about at some point is crucial because some of them may take years to find this solution when problem is complex enough. So in those cases, the heuristic methods came into play. Heuristic can be defined as some cognitive logical function that will try to simplify the problem or direct the algorithm into, well, direction where the solution that is good, maybe not optimal, but at least good enough can be found. So it will allow for a solution to be found much quicker in most cases, but usually the solution will not be optimal. But then again, in most cases, optimal solution is not required. If something is good enough, if it works, then it works. Then we have hybrids. Well, whatever author felt like. That's basically it, because hybrid algorithm will be all in one, will be some mixture, will be everything and nothing at the same time. And types of maps. Luckily, this one is simple. So we have metric and topological maps. Metric maps are basically grids when every cell represents some area in the physical world that in most basic case will be described as obstacle-free or with an obstacle. So it defines regions where robot may or may not go. Then there are topological maps. Those are systems of connected waypoints where those connections maybe not visualize, but state which roads robot could go between which 2 points, okay? And usually those are not physical representations of what the terrain actually looks like, but more like some abstraction of the paths that robot can take, and on practical level, on the real-time navigation, usually metric map comes to play anyway. And also to generate a topological map, I think in most cases that I can think of, a metric map is needed anyway. To get into the algorithm already, because I think I'm a bit out of schedule, cognitive level, this one is, well, if the task is already defined, if the robot knows that it has to deliver materials to Bogdan, what happens next? Agents deployment. So this level, I will only mention shortly because it's a lot to talk about, and also most very valuable materials are directly related to software that is already used with robots, and I couldn't find that much materials about it. So just to give some context, this level will be managing the whole fleet of robots and interconnected machines inside the factory. We'll try to synchronize them. We'll decide which agent should do what. We'll be doing its best not to not create some bottleneck. So basically, it will be managing everything, and then let the lower layers do their job. To go to the global path planning, as I said, usually offline. Obstacle avoidance, where if we already know about them, and algorithms that are used here, well, most literature is about heuristic methods or machine learning methods, because those can be used for quick optimization, and this is really interesting topic for a lot of people, because it is. But also, classical methods can be used here. For example, D-star that I personally really like. I only mentioned machine learning here because it's not really my field, and I didn't want to talk about it in a half-hearted way. But I know something about one of the heuristic algorithms, called ant colony optimization. So the idea here is that we have a nest of ants, an anthill, and a number of ants that will start with going randomly in any direction they want. But then by going in that direction, they will be leaving a pheromone trace. And then when the next ant comes, it will have a higher probability to go the same way because of this pheromone trace than in the direction when there is none. And so there is a video here. I think it was around here. Okay, I will be pausing it. So we begin with a blue anthill, and this green square is food. So the ants should try to find the food and then carry it back to the anthill. So they began with moving randomly, but then when some ants found the food, they're trying to get back to the anthill. And because of those pheromones, they will be developing, well, let's call it corridors. At some point around now, there is a continuous line between anthill and food. And so it's chosen by most of the ants to carry the food through here. And, okay, one important thing here, because it's optimization algorithm, by definition, it should converge to the optimal solution. So in that case, the straight line from anthill to food should be forming. But regrettably, here it's not the case. As the simulation goes, it's the same corridor over and over. So the problem here was in a parameter that is called exploratory behavior. What it means is that when ants found some solution that we can already can see here, they will be going here, okay, but some of them should also still choosing a random direction to go, to still trying to find a better and better solution. But here it's not the case. So it's matter of implementation, but it's important to understand that something like this can happen and will happen in most cases when we are talking about optimization algorithm. Okay. Next one, my personal favorite, the family of Dijkstra algorithm. Dijkstra, in its original form, went like this. We have an initial state where the robot is, and then the target where it should go. And what happens next is searching every cell one by one, beginning with the closest to the initial state until the target is found. So it works. At some point, it will find the optimal solution, but it will take a lot of time, as I will show you in a moment. So then the direct modification called A-star was developed, where a heuristic was introduced. Yeah, and it's an interesting case because depending on the source, this function that was introduced would or would be not called heuristic one. Also, as we can see from, because what this function does is that it will prioritize the points, the cells on metric map or topological map, that will be on the direct line between initial state and target. So it will focus the search area in direction of where it should go. So it will be much, much faster. By definition of a classical algorithm, it will look through everything at some point and will find optimal solution. But there are some people that decided to call it a heuristic algorithm, or at least algorithm with heuristic parts. So there is that one thing that we cannot really, in this field, really fall onto all the definitions. But to say it short, depending on who you ask, you may receive different opinions. Then there is D-star, which is a simple modification where instead of starting in initial state and looking for the target, we are starting in the target and looking for initial state. It's good when we are doing something called reactive navigation, where we don't know anything about obstacles that we can see. We only detect them while robot is already working. And then if we start planning from the target, we have to change only a small part of the path that we have already generated. So it will save us some work. Now another video. Here we have, here is a comparison of work of Dijkstra algorithm and A-star. So based on what I just said, I would like you to watch it and guess which is which. Any idea? Yes, Dijkstra is on the right because we can see that the algorithm on the left, the A-star, after it came out of something called local minimum, I will elaborate later, then it went straight for the target, and the Dijkstra just went on with searching through everything. Yeah, local minimum. So it's again a broad topic, but basically it's some area in search space where, depending on which algorithm you are using, it may fall into infinite loop or it will waste a lot of time. As we can see here, it's an area where from which algorithm has troubles escaping or will decide that because everything around has a higher cost, that I will just stay here and decide that that's the solution. That's why it's called local minimum. Okay. When we're talking about most classical algorithm like D-star, when there is a local minimum, the worst case that will happen in most cases is that we'll waste some time. So here is my implementation. And on the right, you probably can't see, but the target is the red dot on the top, and then we started in the green dot on the bottom. Because this is D-star, the planning process will start from the red dot. So what happened here? Here we have the coast map of the cells that was checked. So we started around here and then went straight line towards the initial state. As obstacle was met, it went around the obstacle and then straight to the target. And the solution was found in under half a second. But then if you swap the targets, if you swap the points, it went straight towards the initial state and into the local minimum area. And before it were overflow from there, it wasted over a minute of computation time. We can omit this because I am a bit late. Local planning. Here we are talking about situation where the robot is already working and we just get into a situation where we cannot continue with the path that we already planned. And here we mostly use classical algorithm as those are much quicker in most cases and much more reliable than heuristic ones. So D star, PRM, D star, RRT. We'll start with RRT. This one I took interest in while developing this presentation. So I already have something from it. Random trees. Talking about ideas here, maybe cumbersome, so let's just go to the video. So what we can see here, just the random tree, the initial one. What can, okay, working with videos is not that easy. So what happens here is that we have a set of cells that are called our tree, the red ones. Then we generate a random point, a sample point, which is green on the right. And then we choose a random red dot and expand the tree from that point towards the sampled one. And so the tree should be growing, but as can be seen here, it's not really growing. Even with generating hundreds and thousands of nodes, the area that was searched through doesn't really expand. So here comes the modification of it called RRT, that stands for Rapidly Expanding Random Tree. And what happens here is that instead of choosing a random point, random red point to expand the tree, we are choosing the point that is closest to the sampled point. So in such a situation, as you can see, the tree is, well, actually rapidly exploring. And this one is already good to use for the actual path planning. There is also the modification RRT star, where difference is that after sampling a point, after expanding the tree, so creating new red dot, we are not connecting it to the one that was chosen before as the closest one to the sample point, but we are looking through all the nodes in some predefined range and looking for the one with the lowest cost. So looking for the one that will be that will lead to the shortest path towards the target. So doing it like this will extend computations for a bit, but will lead to much better solution in the end. Next one. So here is the situation of reactive navigation, where robot was going towards the target, and then it met the obstacle. There was a system that was preventing it from crashing, so it tried to go around the obstacle, but at some point, right here, it decided that it went too far away from the direction of target and turned around. And if nothing happened, it would be going all the way to the right, then back, then left, right, and it's an infinite loop. But in this case, there was an algorithm that was monitoring it, whether the robot was still good to go, or whether it fell into the local minimum. And here's the moment where the monitor decided that it's it's already lost case, the path needs to be replanned. So the path was replanned, and it led to actually successful navigation. Probabilistic roadmap, another sampling-based method. How does it work is we are generating a set of points, and then similarly to a random tree, we are connecting them. But here we are not expanding it from one point, but depending on connecting strategy, we could use a number of closest points to each node. In such a situation, we will get map like this, and it's robust method. It will allow us to go over the local minimum problem, but it has its own issue, because if you are navigating in some narrow corridors, there is a good chance that we will not have any, or we will not have enough points inside such an area to generate a feasible path. There is also a lot of research in that direction. But as we are talking it, we can generate map using PRM, but then we can also connect it with D-star to create a map, to create a path. So it happened here, but as we can see, this path has a lot of maybe unnecessary turns. It's much longer than it could be. So the question arises what we can do with it. Here is a part of my research in the same situation I have showed you before. So on the right, we can see that it was the case where D-star fell into local minima. And looking at calculation times here, well, a quarter of a second, a third of a second, using PRM to generate topological map over this area allowed us to quickly go over the local minimum and find the actual path to the point, to the target. And also, here was used a simple trick to smoothen and shorten the path, because robots always, either mobile or stationary ones, have something called it was next, because I don't want to, permissible positioning error. So basically, it's a range in which robot is allowed to decide that point target has been reached, we can go to the next one. So here by increasing this value, what we did was not to go directly to some points and did all those strange turns, but went into general direction of those, and then far away from them, go to the next one. As such, the red trajectory has been generated, and it was not that much longer, only a few percent, than D-star, which by definition has an optimal solution. So this trick was used on the level of motion controller. Here, most usual ones are APF, standing for artificial potential fields, and fuzzy controller. Fuzzy controller is idea of translating the quantitative values, like electric signals, into linguistic ones. So we don't say that it's 20 Celsius, we can say that it's cold. Okay, 20 is not cold, minus 20 it's cold. And going in that direction, we are fuzzing the signals and then using something called fuzzy rules table. So it's basically a truth table where, based on all the fuzzy signals we generated, we are choosing the most promising answer, which then we are translating into quantitative signal again. So something that the controllers and, I don't know, motors can understand. Potential fields, this one I usually use, but probably not for much longer. Here, the navigation process is based on a superposition of two forces. One is steering robot towards the target, And then there's the other one that will be steering away from all the obstacles. This one was used on the example that I have showed you before. Yeah, it's the APF motion controller is here. Okay, that was the theory, the most general theory of the path planning. And now, before we come back to Bogdan and help to improve his life, I would like to tell you about more or less practical cases that can be found. Traveling salesman problem. This one is pretty popular. Probably most of you already heard about it. So the basic problem statement is that we have basically a topological map, and the question is in what sequence we should go through the nodes to have the shortest path. It's already very complex and interesting problem, but it can be more practical with just a little change to it. So we have something called vehicle routing problem. So the redefinition here is that we are not only looking at how long the path is, but we also have to take into account that the agent, robot, truck, vehicle we are thinking about has some limited capacity. And whether it's loading, unloading, in every point we have into account whether it can continue traveling or it should go back to the depot and unload, for example. But then the problem can get even more interesting because we have something called staying alive path planning. So the definition of the problem here is that, well, as in real life, every robot has some power capacity. When it runs out of power, it just falls down and nothing can be done. So at the level of path planning, we should take into account when the robot should get back to the charger. And this is what happens here. So on the left is the problem solution that we could get if we only talked about the traveling salesman problem. But in the middle, we can see this point in which the prediction was the robot will be left with no power. So instead of such a situation would be allowed to be, the path was changed, and before the robot ran out of power, from this point, it went back to the depot, recharged, and then continued. Reactive navigation. This is one I mentioned before. So the case we are talking about here is that we have not complete or even no information about the environment where we are going in. So the robot has, or at least should be able to navigate in it on its own. And most extreme case is that the waypoint of pre-planned path where the robot should go is directly on the obstacle. So there is no way that it could be reached. There was also the APF controller used. And what could happen here would be that the robot would be going around the obstacle in an infinite loop because it would not be able to reach the target that is inside the obstacle. But there was another controller introduced that based on the dynamic map generated while the robot was working, using something called convex hull, it detected the moment when the probability of the point being on the obstacle, being unreachable, was already high enough, and decided that it's not worth it, let's just go over with it. And what happened here was a quick path replanning. It went again to next waypoint and then straight to the target. Any factory engineers here? Okay, at least some. I was hoping for more. Factorio is an automation game about building a factory, but there are also enemies. And as usually, enemies in games need their own path planning to come and kill you. And the idea here turns out, that the developers actually used A star. A star can be the original implementation of A star can be seen on the left animation, and this is the very nothy case of local minimum, because, well, as you are looking at it, you may even have doubts whether it's A star or Dijkstra. So it took a lot of time to find a path around the lake. And because there are many enemies, many other things that need some processor time to go, they try to modify it. And what they did was generating a path based on chunks. So chunks are, in relation to metric map, we are not talking about one by one cell, but for example, 30 by 30 or 60 by 60. And considering those chunks, they tried to generate corridors that was 2 or 3 chunks wide, and were playing the path only inside those corridors. And using that approach, they managed to cut the calculations time by a few times at least in situations like that. Okay. Coverage path planning. This one is already close to a lot of us because this is the problem definition that is used by autonomous lawn mowers or autonomous vacuum cleaners. So the typical path planning problem is that we need to get from initial state to the target. But in case of coverage path planning, we have to find a path that we allow the robot to cover all his work area, like when moving along. And this problem is actually layers more complex than typical path planning, especially when you want to do it in an optimal way. There is a lot of research in that direction, especially when we are talking about autonomous agriculture implementations. This is really hot field in recent years, and well, not without a reason. And in this case, as you can see, there are parallel lines called Bustrophodon lines in play, but optimization can be seen in angle in which they are generated, because every field has some slope, has some difficult terrain parts. So the question is how machine should approach it to spend the least amount of energy. Also something more about optimization and machine learning techniques. Very interesting problem of generating an optimal deployment strategy. So if we have some coverage path planning task, we have multiple robots, then the question arises, which area, what trajectory every robot should go to complete the task with the least amount of time and least amount of energy. Okay, so back to the Bogdan. We already understand how path planning works and how we can approach this problem. So using this knowledge, we were able to generate a path that went around that avoided all the obstacles and allowed the robot to deliver his payload, and well, now he's idle, or not really, because the life of robots is full of work as ours is. So only a quick mention in the end, because for the whole presentation, I talked about mobile robots, because this is usually the topic that you expect when we are talking about path planning. But the path planning exists also when we are talking about manipulators. Usually, we don't have to take it into account, because when you're talking about robot cells, it's usually space as obstacle-free as possible, maybe some regions where robots cannot go, and we just don't care about those. But in some cases, we also have obstacles here. And the path planning can be used in the same way when we are considering manipulators, and we need to make sure that it will not hit any obstacles. So that will be it. Thank you for your attention. I think I am on time. You are?
Well, I mean, like, we
For-
still can have few minutes for questions, obviously, because yeah, that was great presentation. I hope you have lots of questions. So who's first? And yeah.
So what is a practical use case for those algorithms? Because from my experience, the Dijkstra is enough for most. So is it in games or where actually there is a need to develop better algorithms?
Dijkstra, by definition, will find the path, and it will be even optimal under some constraints. But the problem here is the computation time, because as you could see on the animation, when we compared Dijkstra and A star completed its job like 2 times faster, something like this. And in every case, whether we just playing around, developing games, programming the robot, in any case, if we can cut down the computation time, we do it. Because then we have more computation power for different algorithms, new solutions to make all the work safer, or we can just work faster.
I have a question because there was gate visualization, and to visualize this algorithm, you almost always present in 2D. And I think that there is some cases when the robot have more degrees on freedom. Do you have some hierarchical pathfinding that you have 2D path, or you have more dimensional pathfinding?
There is also a lot of work when it comes to pathfinding for drones, so in 3D. I usually stay in 2D because it's more related to industrial robots that I have to deal with. But when we are talking about path planning in 3D, you can use all the same methods, mainly just modify an implementation for a bit to work in 3 dimensions instead of 2, but all the methods will be the same, all the problems, consideration, etc. will be the same, or at least they should be. Complexity will be higher, yes, because instead of 2 dimensions, we have 3. But when it comes to planning the algorithm, how it should work, the problem definition should be around the same. So the main difference will be amount of computations that you require to solve the task.
Hello. Do you have a comparison with RRT star with PRM D star that you made?
PRM D star and row D star, there should be somewhere. Yes. This was the very specific case because I intendedly designed it to show the very no-fee local minimum problem. And in this particular case, the row D star is the first line. It took around 73 seconds to complete the path planning. And PRM D star without the motion control smoothing took around 1/4 of a second. And yeah.
Sorry, I meant RRT star. RRT.
RRT, yeah.
Yes.
I don't have this one. RRT was something that I researched only on Saturday while preparing for today, but probably I will get back to it at some point, but not for now.
Hi, what do you think is more generic solution to find the path like on this 2D map, or to initially make a graph and then search the shortest path of graph? I'm asking like, is this graphing of the map, in what cases is it optimal, when to use it?
Sorry, could you repeat the first part of the question?
Yes. So when you said we have 2 kind of algorithms. One when we have 2D map of the surface with obstacles. And the second one, like that it is analyzing the map and creating a graph. Yeah, and then we are looking for the shortest path in the graph instead of the map. So which solution is better, or maybe in what situation, which one to use?
It depends.
Okay, so on what? It
That's
depends on
always
what.
the answer.
Yeah.
The case that we can talk about here is in the factory when we have a fleet of logistic robots. Because the environment is changing, we don't really usually have the means to constantly update the metric map. And what we could do is use the topological map that will be, in a sense, a generalization of the actual outline of the factory. So if we assume that going from point A to point B will cost us, I don't know, 100 seconds, then in real case, it will be something around this, but the computation times will be much, much lower. So it's like simplifying a problem through reasonable means. And it's also totally applicable because if you are talking about the real optimal solution, then we usually only stay in the environment of simulations and theoretical thinking, because in practical application there are so much things that could go wrong that the optimal solution will be basically never realized. So using topological map is simplification that will allow us to shorten the computation time and will give us a solution that will be fully applicable and feasible.
Okay, so it's in most cases it's better to create a topological map.
Depending on the case.
Okay.
The one we talk about, yes, I believe topological map will be better.
Okay, but for example, if you have unknown map, it's not better, yeah?
Well,
if we don't have map of obstacles and we will find them on the way.
Yeah, the case I was talking about was going back to the presentation at level of global path planning. So we decide what the robot should do to perform the task. But then it's already running and it's detected some obstacles. So in this case, we are going lower to the local path planning, and then you basically have to use the metric map, or at least it will be, in my opinion, a bit better.
Okay, thanks.
Okay, so let me ask about, you presented this theoretical part really nice and explained most of it, but how does it correlate with the spot sitting next to you? Have you tried applying some of those algorithms on it and testing in real environment, or was it all just simulation and you persuaded someone to buy spot just for fun?
With my colleague here, we already have something in motion. Not him in motion. We have something in mind to prepare a logistical robot-like task for the spot, but the path planning on our side will be at the level of global path planning. And how this gentleman here navigates is in the basic case from, well, let's call it QR tag to QR tag. This is the basic task, the absolute localization. Okay. But how he does move is entirely on his own. It is embedded inside his firmware, and we don't really have a possibility to modify it in any significant way. So the best thing we can do is to think about and modify the set of points, a sequence of points that he should perform.
Okay, I have like a minor question. Like, have you, while doing all this research, thought like maybe why don't I just use a large language model like ChatGPT, just give it an image and say like plot the shortest, draw me the shortest blue line from this point to this point?
Back when I was writing my master thesis, I spent a lot of time playing around with heuristic algorithm and trying to optimize everything. But the first first thing that I realized is that it's simple, it gives me solution, but it's not only takes a lot of time, but it's also not funny. I much more prefer working with classical algorithm, not optimization ones, because there is a lot to do with maybe implementing some heuristics to it to try to find the way even faster, but still retaining the full control of what is happening, not relying on the convergence rate and all the scary things from stochastic algorithm. And also try to run the computation time as low as possible. But maybe that's just my thing, because I work a lot of microcontrollers. So optimizing every processor operation is just my little thing.
All right, there is a question for me. Thank you for such informative presentation. Questions relating to all algorithms which you mentioned. There are lots of algorithms, lots of possibilities to plan the path, which you can do with robots, maybe in games, maybe in other manipulators. Have you, during your research, have you found and noted how much of these algorithms are used in practice?
D star or A star are used all the time, both in industry, in games, in simulations. It's one probably most popular of classical algorithm, because as far as I'm concerned, random tree are less commonly visible. And when it comes to heuristic algorithm, the most popular one is genetic algorithm, definitely. It's the one that I see most often. And then there is a lot of ant colony optimization. But the little differentiation, genetic algorithm is used everywhere, like really everywhere. And ant colony is mostly used straightly for path planning. I didn't see it much in other implementations, but maybe I just wasn't looking deep enough. I want to mention here also machine learning. As I said, it's not really my field, but even I have seen that there is a lot of it in path planning. But the way it works is, I think, similar to heuristic algorithms that do the optimization. So among those that I have told you about, D-star, genetic algorithm, or ACO, and then from motion controllers, fuzzy one is the most popular, because there is a lot of space to play with optimization, machine learning here. So there is a lot of options to get creative.
All right, thank you very much.
So, okay, once again, you are faster than me and applauding him. So that's great. Thank you. So yeah, that was a great presentation. Let's be fair. Also, once again, thank you for all the questions. And what else? So that's partially the end. Right now, we will be moving towards the lightning talks. And if anyone is feeling about talking about something they want to say us, go on. No?
Even 1 minute or 10 seconds,
Yes, not really. So wait, we come here because I think are we running out of time or not really? Okay, so turns out that we're actually running out of time because yeah, okay. So there will be no lightning talk. Sorry, it's just a little bit of misfortune communication. Anyway, so thank you again for coming here. Right now, we will be we'll have the time for a beer and for chat. Once again, you can check out the robot once again, play with it if you want, and if Bartek will let you. So yeah, we will be around like for the next meetup.
It should take place at the end of February, at the beginning of March, somewhere around this time. So stay tuned for more information. Check our social media, check our LinkedIn, our Meetup page, and Facebook, and you will find all of the information you need to know where the next meetup is going to happen. And also, if you have a interesting topic you want to share with other people, feel free to reach us, and definitely we can arrange some time for you during the next meetups to present. So yeah, once again, stay tuned and have a nice time.